So, we are going to continue with what we have done, what we are doing. So, we have obtained a limiting solution for this special case when the penetration depth, when the penetration of A in the liquid is not too high, too large, which would be the case if it's if the contact time between A and the liquid B is short. So, this is the error function solution, and the examples of error function solutions can also be obtained when it's about the velocity when a plate in contact with the liquid is suddenly set in motion, or you can see it in heat transfer as well when a block which is maintained at a uniform temperature, one end of which is suddenly exposed to different temperature, and you are trying to find out how the temperature inside the solid object change as a function of distance from this surface and as a function of time. In all cases, the form of the governing equation would look like this. So, and the initial and the boundary conditions are also. So, the initial condition for these two cases should be at t equals 0, that means at time equals 0, the velocity is 0 at any y, and the two boundary conditions which are relevant over here is, as you can see, that at y equals 0, no matter whatever be the time, the velocity is simply going to be equal to the constant velocity v with which this rod is being pulled, this plate is being pulled. So, at y equals 0, for this case, if this is y, at y equals 0, the velocity is going to be equal to capital V. And if you go to a distance far from the solid plate, there the fluid still does not know that there is a plate and it has started moving. So, at a point far from the wall, which is this, the velocity, the concentration, the equivalent of concentration in that case would be the velocity would still be 0. So, this is identical with what we have written here in terms of the boundary conditions, and when you think of the temperature, when it's one end is suddenly changed, you know that at z equals 0, the equivalent of that in this case is time t equal to 0, the dimensionless temperature, the way we define it, the dimensionless temperature is 0, so or T is equal to T I. So, T minus T I is going to be equal to 0. At x equals 0, that means at this point the temperature is going to be equal to T 0, the new changed temperature which remained constant. So, at x equals 0, that means on this plate at which the temperature has changed, it is a constant, and since if you move far from the wall, from the face at which the temperature is changed, the temperature there will still remain equal to T I. So, the dimensionless temperature would be equal to 0. So, I would advise you to see these three problems together and see what is the similarity between the governing equations, the coefficients. Important is the transport coefficients which arise automatically in the governing equations. Look at the similarities between the initial condition and the boundary conditions, and for one of them follow the solution methodology. So, once you have the same form of governing equation, same initial and boundary conditions, then the solution obtained in one can obviously be written as the solution of the one that which you are dealing with, provided you change accordingly. For example, velocity, dimensionless velocity would be replaced by dimensionless concentration, the time would be replaced by x at z in this case, time would be replaced by z in this case, and the boundary conditions are at x equals 0 and x equals infinity. And the transport coefficients, which is DAB for the case of mass transfer, when you do it for plate suddenly set in motion, you would see that it is going to be mu by rho, or the kinematic viscosity. And when you write it for the, when you look at the expression, when you look at the governing equation for heat transfer, you would see that it is going to be alpha or mu by rho Cp, that is the thermal diffusivity. So, these three equations, these three situations and these three equations will not only give you identical conditions, boundary conditions and initial conditions, it would also identify the transport coefficients of interest, of relevance in these problems, namely the diffusion coefficient, the kinematic viscosity, and the and the thermal diffusivity all having units of meter square per second. And any one solution if you follow, you should be able to write the solution for the case at hand using the same steps. So that's why I am not solving the problem, I am simply writing the final form of the solution based on our knowledge of the previous cases. So here we have the limiting solution, and we would like to find out what is the total mass transfer rate. That is the important one which we wanted to find out, mass transfer rate. And the total mass transfer rate, in order to do that, I would first find out what is the local mass flux. So this is N of A, component A, it's in the x direction, which is a function of z. We are evaluating at x equal to 0. So I am trying to find out what is NaX that enters the film, which is a function of z. At different points this NaX would be different, but I am going to do that at one plane. So coming to the larger picture, this NaX, it varies with z, but I am evaluating this NaX at x equal to 0. So I am trying to find out what is the mass flux across the liquid vapor interface, and therefore this would simply be equal to minus dAB del Ca by del x at x equals 0. So the flux of A in the x direction at x equals 0 would simply be equal to minus dAB del Ca del x at x equals 0. So that's straightforward from the Fick's law, from the definition of diffusive mass transport. So I will write it again, NaX at, which is a function of z, evaluated at a specific x, which is the liquid vapor interface, would be minus dAB del Ca by del x at x equals 0. So this would, when I substitute Ca from this error function form, what I am going to get is equal to Ca naught dAB del x of error function x by root over 4 dAB z by V max at x equals 0. So this directly is formed by putting the expression of Ca from here to this point and then performing the differentiation. So this 1 would go away, and you would simply have del x of error function of this evaluated at x equals 0, and that's what I have written over here. Now one of the properties of error function is del x of error function x by root over 4 a z at z equals at x equals 0 is equal to 1 by pi a z to the power half. So this is one of the relations of error function which are available. So I am going to use this relation in this. So my NaX at z at x equals 0 would simply be equal to Ca0 d times dAB V max by pi times z. So when I do this, so my A is simply, if I compare between this and this, my A is simply equal to dAB by V max. So this with this formula which is provided, I can write my the local mass flux at x equals 0, which is a function of z, and this is expressed in this form. So the total moles of A transferred per unit time is simply, if I express it as W A, to be 0 to W, 0 to L, N A X with at x equals 0 is the same thing, and x as a function of z at x equals 0 times dz dy. So, this is the mass flux of A, species A. This is the flux of moles of A getting into the x equals 0 plane, and we understand that this could be a function of z, which is shown over here. Now, in order to obtain the total moles which are transferred, I am going to integrate it over the entire area of this face, entire area of the x face, which is from y, the integration of y and integration of z. So, the y integration is from 0 to w, and the z integration limits are going to be from 0 to L. So, that is why it is integrated over 0 to L dz and 0 to w dy. And we understand that this NaX is a function of z, but it is not a function of y. So, when you perform this equation, you would see this is going to be C A naught root over 4 d A B V max by pi L. So, this is then the number of moles of A which gets transferred from the gas to a falling film of liquid, but with some assumptions. So, what are the assumptions? Let us recapitulate once again. The assumptions that we have used are, it is one dimensional laminar flow, the contact time is small. So, A does not penetrate to a greater distance, to a larger distance into B, and it's falling in, it's a steady state process, and the diffusion of A in B is a slow process, and therefore, we could make certain simplifications of the governing equation based on what is important in which direction. So, we understand that diffusion is the only way by which mass gets transported in the x direction. We have both diffusion and convection in the z direction, but the convection overshadows the conductive or diffusive mass transport in the z direction. Then we have obtained the governing equation and identified the boundary conditions. But we have, if we have used the condition of very small contact time, then what we would see is that the A does not penetrate much into B. So, for the diffusing A molecules, the other end, the solid wall, is as if it stays, it is at infinity, it is at infinity. And since it is only diffusing by a small distance inside the liquid, to all diffusing A molecules, it would seem as if the entire liquid film is falling with the velocity equal to V max. So, a further simplification of the governing equation and a further simplification of the boundary conditions are possible, which would make them identical in form and in governing, in form and in boundary and initial conditions, two situations for which analytic solutions are available. So, we get an error function solution, and using the error function solution, I can obtain what is the flux of A molecules onto the surface of the liquid, and integrating this flux over this entire area, that is from 0 to L and from 0 to W, I can obtain the total number of A molecules, total number of molecules of A which gets transported, which gets absorbed by the falling film of liquid. So, this expression which we have obtained finally is relevant in many falling film devices, where a gas is going to be absorbed on the liquid film, and it is a nice example to establish the utility of using species balance equation rather than the shell species balance. So, from now on I think you would be more comfortable in using this equation for all your subsequent analysis. So, what I would do next is a very quick problem, tutorial problem on mass transfer, and which would again which would give you some more ideas about the use of error functions, the differentiation of an error function, and how you can use a mass balance in order to obtain some expressions in a valid engineering problem. In an engineering problem, what you are going to find out the rate of decrease of a layer of a slab of salt which is kept in contact with a water. So, I have a slab of salt and a body of water above it, but they are separated from each other by another plate, another impervious plate. So, what is going to happen at t equals 0 is this plate which separates the salt slab and water, it is removed. So, now the salt slab is in contact with the water. So, initially the water does not contain any salt, but as time progresses the salt from the interface is going to get into the water, and therefore, the concentration of salt in water is going to increase with time if you fix the location, or the concentration is going to be a function of this direction. That means, as you move far from the slab, the concentration of salt will progressively decrease. So, it is a case of concentration varying with time and with position. So, a salt slab suddenly brought in contact with a deep pool of liquid, and we have to find out what is the how does the concentration of salt concentration changes in the liquid, and what is the recession rate. That means, as time progresses the salt slab is going to get thinner and thinner because it is getting dissolved in water. So, what is the rate of recession, that is d, if L is the thickness of the salt slab, what is dl dt, that is rate of recession of the salt slab as a function of time and other parameters. So, very quickly what we have then is, this is my salt slab and we have water present on top of it. The concentration of salt in water at 0 time is, we call it as rho a I, which is equal to 0. The concentration of salt at the interface at this point is equal to 380 kg per meter cube, which could be the solubility of salt in water, and the solid salt slab, the rho a of the solid, this is the salt slab, is equal to 2165 kg per meter cube. The DAB, that is the diffusion coefficient of salt in water, is 1.2 into 10 to the power minus 9 meter square per second. So, this is your water B and salt is A. Okay. And what you have to find out is how does the concentration of salt varies in water and what is the rate of recession. So, this is initially the thickness is L. We will assume that this is my x direction, and I would like to find out what is the recession rate, that is dl dt. How does the thickness of the salt slab change with time? So, as before, I can clearly write that the governing equation is going to be equal to, so DAB is equal to del rho A del T. So, this if you see is identical in sense to this equation. Okay. So, change in salt concentration, if you you start with the equation, that is del rho A del T plus Vx and all these terms is equal to DAB times del square rho A del x square plus same thing del square rho A by del y square plus z square plus a reaction term. So, there is no question of velocity in here. So, the entire convective term would be 0. The rho A, the salt mass concentration of salt is a function only of x, it does not depend on y, it does not depend on z, and there is no reaction term. So, your governing equation would simply be del rho A del T is equal to dAB times del square rho A by del x square. So, quickly you can obtain what is your governing equation, and the initial condition is this, that is rho A at any value of x at 0 time would be equal, if I call it as rho A I, this is going to be equal to 0, and the boundary conditions that you would get is rho A at infinite x, that means at a point far from the interface for any value of time would be equal to 0. So, there is no salt present in this water, and rho A at x equals 0 for any time x on this surface, but at any time must be equal to rho A s, which is the concentration of salt in the liquid. So, this is equal to rho A s. So, in terms of IC, BC and the form of the equation, this is the same as this equation. Okay. Only thing is this V max in here is 1. So, if you compare between the forms of these two equations, they are same. The initial conditions, the boundary conditions, the initial conditions and the boundary conditions, they are the same. So, you can directly write for such problems, you can directly write what is going to be rho A as a function of x and t by rho A s, which is the one which you are using to non-dimensionalize the mass concentration, is 1 minus error function x by 2 dAB times t to the power half, previous solution that we have obtained for this case. So, this is part A is done. Now, we are trying to find out what is the recession rate. So, we make a mass balance of the salt. Some of the salt is going to get dissolved, as a result of which the amount of salt present in the slab is going to get decreased. So, if I express it in terms of an equation, the rate of mass of A which is going out must be equal to the m dot A which is stored in the system. So, we do not have any salt coming in, the salt is going out. As a result of salt is going out, the amount of mass of salt contained in the slab is going to be reduced. So, the equation in this form is m dot out is equal to m dot stored. A refers to salt. So, out is equal to stored. So, which we, if we take an unit surface area, so mass flux of A of the salt is equal to d dt of rho A s times L. This is the species mass flux at the surface, and what you would then get is when you perform this d dt, and we know what is the expression of rho A from here, and I know how to differentiate the error function and find out the value at x equals 0, that at x equals 0, then you can simply directly write as n A double prime s is equal to dAB rho A s by pi dAB times t to the power half. I have used the formula that d dx of error function of x by 2 dAB t to the power half evaluated at x equals 0 is equal to 1 by pi dAB t to the power half, standard formula that I have used. So, this is the formula, and so here I have evaluated the left hand side, and when I go to the right hand side, I simply get dAB rho A s by pi dAB T to the power half is equal to rho AS comes outside since it's a constant times dl dt. Okay. So, this with a minus, since I started with a minus, expression of ns is this, and so therefore, this equation now becomes this is equal to rho AS on the outside times dl dt. Now, you can quickly integrate this. So, you get delta L over time, you get delta L is equal to minus 2 rho AS by rho A of the solid salt times dAB T by pi to the power half. So, it's given that the when you plug in the values, 2 will remain as it is. Rho AS is 380 kg per meter cube. Rho A of the salt is 2165 kg per meter cube. The value of dAB is 1.2 into 10 to the power minus 9 meter square per second. Time is 24 hours into 3600 second per hour divided by pi to the power half, and what you would get is 2.02 millimeter. So, over a 24-hour period, the salt slab will be reduced by the size or thickness of the salt slab will get reduced by about 2 millimeters. So, let me quickly go through it once again to show what I have done. On an unit surface area, based on, first of all, I have obtained an expression for the concentration, which is in error function. Then I have made a mass balance across the salt slab. The one that goes out, it goes out by dissolution into water. This is going to make a change in the stored amount of salt in this. So, this is my governing equation. When I express in terms of an unit surface area, so the area will cancel from both sides. So, what I have then is the mass flux of A which is at the surface is equal to d dt of rho A of the solid salt times L, and the area simply gets cancelled from both sides. So, my mass flux can be written as dAB times del rho A by del x at x equals 0 with a minus sign. So, this del rho A del x at x equal to 0, I already have the expressions for rho A in terms of error function. So, I am trying to find out what is del rho A del x at x equals 0, and I use the formula which I have shown you in the previous example. So, I have a compact expression for this as well. So, the flux, the mass flux is evaluated as using this formula as this. So, my minus Na double prime S becomes minus this dAB rho S by pi dAB T to the power half. Please do it yourself and verify that you are getting the same answer following the example which I have shown you before. And this differentiation, since rho AS is a constant, it comes outside. So, it is dl dt, and then you integrate it once, and what you would get is delta L from. So, you integrate it from 0 to t and from 0 to L. This is the expression which you would get, and when you plug in the numbers, you would see that the thickness of the slab decreases by about 2 millimeters over a 24-hour period. So, what we have done in these two classes, showing the utility of the use of species balance equation, identifying that error function appears in many problems of heat, mass and momentum transfer, utilizing the property, the mathematical property of the differentiation of error function at x equal to 0, at t equals 0 at some specific point, we can obtain, in the last problem we have obtained the surface recession rate of a salt slab. So, through theory, examples, we have established mass transfer, the ways to model mass transfer, the use of species equation and complicated situations. in mass transfer. So now I think we are in a position to get into the analogy part, the last remaining part of transport phenomena. Can we compare mathematically utilizing the similar nature of the governing equations and similar nature of the boundary conditions, the coefficients, the relations of heat transfer in mass transfer? What needs to be done? That is the topic, that will be the topic in the remaining classes of this course.